All right, one last topic that I want to cover before we move on from memory allocation is the other way we do memory allocation in addition to manual allocation. In fact, the more common way we do memory allocation, which is garbage collectors. So I've got some slides here that cover the basic concepts of garbage collectors pretty effectively, and we're going to go ahead and run through them. Now, at this point, we've talked a lot about how to implement malloc and free. That's the normal way to do manual memory allocation. That's how it works in C, and it works pretty much the same way in C++. They're called new and delete instead of malloc and free for the normal way to do it. It works pretty similarly in a couple other languages, D, Rust, some versions of Fortran. You get into weird languages that nobody uses anymore, like Forth, but a bunch of languages do this sort of manual memory allocation, but they're mostly old or sort of weird low-level languages. We talked about how we can do that with a free list, or we can do it with either something like a buddy system allocator or a bucket allocator, and some other ways to optimize. But for most languages, especially languages that are trying to be sort of easy to use and not necessarily focusing on super high developer controllable performance, or the ability to do system sort of stuff like get pointers as integers and then manipulate them, we're more likely to use garbage collection. So this idea of garbage collection was invented in the late 50s. So that was an awfully long time ago, 1959. And that was initially developed as a feature for the Lisp programming language. And the general idea is that we're going to have some automatic system that's going to go figure out which objects have been allocated but are no longer in use. And we're going to call those things garbage. Figuring out what in use means is kind of tricky. So we have a more specific thing that we're going to look for, and that is objects that can no longer be accessed. The way we tell if an object can be accessed is if we still have a reference to it. If we're thinking about C, that means we still have a pointer to it. So if we've allocated an object with malloc, and then we got the pointer back, and then we lose the pointer, we assign some other value over that pointer, a garbage collector would say that object is now garbage, you can never use it again, so it's safe to clean it up and free it. Turns out this is a little bit tricky to implement, although it is the most common way that memory gets managed in modern systems. So here's the broad idea and the sort of key concepts that we're going to need in order to make this work. We have our heap, and we have some root nodes. And the root nodes are things that aren't on the heap, but are things that we know are places that the user could have stashed a pointer or a reference to a heap object. And so these are the places that we have to look to figure out, to get started with this question of which objects are still reachable. Now, once we've started scanning at the root nodes, we may have to recursively traverse a bunch of objects on the heap to figure out which objects are indirectly accessible from the roots. And right here it shows this the way it normally works, which is that the main root nodes are global variables and then local variables that are currently on the stack. Those are the places that might have references to the heap and might be keeping dynamically allocated heap objects alive. Stuff that isn't connected to the root nodes at all, stuff that we don't have a reference from the root to, or a reference from the root to some object that then indirectly through some chain has a reference to these objects, we call those garbage, and we can safely clean those up. Now, if we're going to try to do something where we're going to build a garbage collector in a language with pointers, like C, like the way we've been dealing with programming all semester, we have a sort of annoying complication. And that is that we're allowed to have things that are pointers, but aren't necessarily marked as pointers somehow. And even better, if we're actually concretely in C, we have this problem where the compiler throws away all the type information. So like here we have this variable that's marked as being type int, and the compiler knows at compile time that the value in x is an integer, but at runtime that information has been thrown away. We no longer can differentiate between x, the integer, and x, the pointer. And in this case, we're thinking about a 32-bit machine, as we do in these slides I stole from Christo. So this thing looks entirely like a potentially valid pointer. It's a 32-bit value that isn't like under 4K. It's on the first virtual page where it's unlikely to be a pointer. So that might be a pointer. So we have to try to figure out which things are pointers. And there's two ways to do it. Plan B, and what we would do if we actually wanted to build a garbage collector for C, is we're going to go ahead and assume that anything that looks like it might be a pointer is a pointer. So we'll scan through the stack, looking at all the things that are on a 64-bit system 8 bytes long, so that's the size of a pointer, and aligned at 8 bytes, that's a restriction that we have on a 64-bit system, is that pointers are always going to be 8-byte aligned. And so every single value in the range of memory that is the stack that is one of those, we'll go ahead and start by assuming that it might be a pointer. And then we ask, does it point into the heap? And if it does, then we just assume it's a pointer, and we are going to go ahead and make sure that any object that it's pointing to isn't an object that we're going to delete. The more common approach is we use a language that has a type system that allows us to track the types of things at runtime. So for example, in Java, the way you define new types is you define a class, and the way the Java virtual machine represents classes makes sure that it can differentiate which fields are references to other objects and which fields are just integers. So if we have a field that is of another class type, that's definitely a reference, and when the garbage collector is scanning through the heap, it can go ask which fields of the object are references. They're represented in memory the same way that pointers would be represented, and it will go ahead and use those as pointers and not use the things that aren't pointers, and not try to treat random stuff that isn't pointers as pointers. And Crystal likes the plan with the type system better. All right, so there's two general approaches to this sort of automatic memory management. The common one that most languages use is mark and sweep, where we will go ahead and start at the roots and try to find out which things are still alive, mark them as being alive, and then clean up all the things that we couldn't demonstrate to be alive. The other option, which is used in some programming languages and is a trick that we can use to solve some cases where where manual memory management with malloc and free doesn't really work, is this idea of reference counting. So we'll look at reference counting first. These other two things, copy collection and generational collection, are just enhancements to the mark and sweep idea. All right, so reference counting, we're going to modify every object in our system, or at least every object that is being memory managed this way, by adding an additional field called ref count. And that ref count is going to be an integer that's going to keep track of how many pointers there are to the object. How many variables do we have that point to the object? How many fields on other objects point to the object? When we allocate the object, the reference count is going to be 1, because we called some function to allocate it, and then we're going to assign the result to some location, a local variable or a field, and so there's 1 reference to the object. Every time we make a copy of that reference, so every time we assign that local variable to an object field, we're going to have to increment that reference count. If we're doing this in C, we may actually write this code manually. If we're working in a programming language like Perl that uses reference counts as its garbage collection mechanism, the language handles dealing with the reference counts for you, but every time you make a new reference to the object, you have to make sure you increment the reference count. Every time you eliminate a reference to an object, so overwrite a local variable, have the local variable go out of scope, overwrite a field on an object, have an object get cleaned up because it is now garbage, you have to make sure that you decrement the reference count to the object that lost a reference. And then when that reference count goes to 0, we know it's garbage and we can delete it. So here's an example. We're going to go ahead and like malloc an int, and the 1 here isn't the value of the int, that represents the reference count. If we go ahead and create another object and have that global variable p point to the new object, that means that p is no longer pointing to this old object. So when we change where that variable is pointing, we're going to decrement the old reference count. Now that brought it down to 0, and that means that we can now free that object. If we have an object that we're referencing from the stack, we can go ahead and have the reference count be the number of local variable references that reference the thing on the stack. If we pass that thing to another function, then when we pass that to another function, the local variable in the second function, or the parameter variable in the second function, is going to be a second reference to the object, so we'll increment the reference count. If we pass it to a third function, that local variable is a third reference, we increment the reference count. When we return, a variable goes out of scope, so we decrement the reference count, return again, a variable goes out of scope, and then eventually we will overwrite the original reference with a new value, and that's going to remove a reference to the original object. We decrement the reference count 0, we can free it. So if we have a linked list, the head of the linked list, this first item, is going to have one reference to it, which is this global variable named head, and so it's going to have a reference count of 1. It points to another object. This pointer in the first object is a reference to the second object, so the second object has a reference count of 1. Third object has a reference from the second. Fourth object has a reference from the third. Now, if we were to have head, like assign 0 to head, that would remove the reference to the first object, decrement this reference count to 0, and we could clean it up. When we cleaned it up, that would decrement this reference count to 0, so we could clean this up. That would decrement this one to 0, we could clean this one up, and that one could decrement this one to 0, we could clean that one up. And the result would be that a reference counting system would handle this linked list nicely. Unfortunately, there's a problem with reference counting, and that is that. So take a second and think about why that might be a problem with reference counting. Here's the problem. If we overwrite that head pointer, we decrement the reference count. So we had two references. We had the global variable, and then we had the last item in the list, which were references to the first item in the list. We remove the only reference from the roots, and all of these objects still have non-zero reference counts. There's no way that we can access them. That means we just leaked memory. And that's a problem with reference counting. Whenever we have a circular reference, that potentially means that if we lose our external reference to that circular reference, it will just keep itself alive forever, and we aren't accomplishing our goal of avoiding memory leaks. Well, one of our goals of avoiding memory leaks, because we can still leak memory if it's circular. And when we're working with reference counting, we have to keep that problem in mind and manage it manually. Before we overwrite the value here to head, we have to remember that this was a circular linked list and overwrite one of these references so that we just have a non-circular list that will get cleaned up when we zero it. There's also some concepts like weak references that are worth Googling that help solve this problem, but in general it is a real problem. The one language that I can think of, the one programming language that I can think of that uses reference counting as its primary mechanism for garbage collection and doesn't have some cheat to try to avoid this problem is Perl. And in Perl, if you build yourself a circular linked list and then lose the reference to it, you just leaked memory. You have to remember that property of the memory management in the language. So, according to Christo, the trade-offs here for reference counting are that it's good because it's simple and it's easy to understand. And that's true for the simple versions of it. you can get reference counting to be awfully complicated, at which point it doesn't have these advantages. The disadvantages, the big one is that we have this circular object problem, where if we have a cycle in our object graph in memory, reference counting will no longer free all memory when we lose our references to things. But there's a couple other disadvantages here. For example, we have this reference count that has to appear on every single object. That's a complication in two ways. It's taking up memory and performance, but it's also meaning that if you decide to use reference counting as your mechanism for memory management, that's constraining your program design to require you to have this field on every object, and that's potentially inconvenient. You can have sort of reference count only objects where you have a reference counting object that has a reference count in it, and then it has a reference to the actual object, but then you have to allocate 2 objects for every 1 object, and that's a disadvantage too. Another really big complication in practice with reference counting is that if you get into multiple threads, this reference count field in the object is going to be shared mutable state, and the reference count gets mutated a lot. Every time you assign a reference to this object to a local variable, you conceptually at least have to increment that reference count. When that goes out of scope, you have to decrement that reference count. And if you're doing this with multiple threads, you have to think about, do we put a lock on that? Well, hopefully not. We can use atomic instructions, but atomic instructions are kind of slow. And in fact, they're slow enough that we don't necessarily want to be doing atomic operations every single time we assign a new reference to a variable. So these are design issues that have to be dealt with if you're going to be taking advantage of reference counting as your memory management system, garbage collection system overall. All right, so the standard version of garbage collection is this idea of mark and sweep. Every once in a while, for example, when we run out of memory, at least run out of memory on the heap and have to consider growing the heap by requesting more memory from the operating system, we're going to scan all the objects that we've allocated to see if they're still alive. We'll start at the roots. We're going to look for all the objects that we can reach from the roots by traversing this sort of object graph. We're going to mark every object, and then every object that didn't get marked is going to be garbage. This mark field might be in the object header for an allocated object, or there might be a array of marks somewhere else. Those are implementation details, but we have to have at least a single bit for every object that we can use to mark the objects. So here's what that looks like. We have our heap. Some of these objects are clearly still alive. Some of them don't have any references. And so we're going to start at our roots. This is a global variable. It points to this thing on the heap, so we'll mark it. This is a global variable. It points to these things on the heap, so we'll go ahead and mark those. This is our stack. So we're going to point, which points to those 2 things on the heap, so we'll mark them. All the stuff that isn't garbage is marked, so then we do our sweep phase, and we sweep through our entire heap and free all the objects that weren't marked. If we look at our problem that caused issue, or our setup that caused issues for garbage collection, or for reference counting, we can do the same thing. That's reference from the heap, we mark it. This doesn't point to anything, it must be null. The stack references these 2 objects, we'll mark them, then we go ahead and sweep, and it turns out that nothing marked that circular list, so there's no reason it's not garbage, and so we just clean it up. So we handle cycles correctly with mark and sweep. So this is a nice system, it's something that we've been using since 1959, and a big advantage is that it solves most of the problems that we had with reference counting. We no longer have to worry about cycles not getting collected, and it's still relatively easy to think about and implement, although it's not as simple to implement as reference counting. But there's some disadvantages. The first disadvantage is that we have to spend CPU time doing these mark and sweep steps. This means that whether or not we're actually trying to free any objects, every once in a while we're going to stop what we were doing intentionally in our program and instead go do this garbage collection thing. And that's going to be sort of logically a linear time operation based on the entire size of our heap, all allocated objects. In fact, not even just all allocated objects, but all objects that have been allocated for the entire life of the program that haven't yet been freed. So both allocated objects and garbage objects. We have to scan all of them. And it's sort of tricky to try to do this with threads. So a sort of standard implementation of this is going to either mean that our program doesn't have threads at all. That's how some scripting languages like Ruby handle this. Or if we do have threads, we have to have some mechanism to coordinate all of the threads stopping so that then we can run the garbage collector. And even in like very advanced systems like Java, we still end up getting efficiency gains from stopping all the normal threads and then running the garbage collector without any of like the code that the user intentionally wrote running at the same time. This creates garbage collection pauses. And there's complications. Now, this is an important point. Even with mark and sweep garbage collection, we can still have memory leaks. Not in a sort of technical sense of like not collecting stuff that we've correctly told the machine it should collect, but in the sense that if you have a global like vector and you push everything that you allocate onto that global vector, none of that's going to get garbage collected because there's still references to it. All right, so let's try to optimize this mark and sweep plan. And sort of the key development in how we can optimize this is this idea of copy collection. And the big annoying thing about mark and sweep is that we have to scan every object on the heap after marking to find the garbage. And another neat thing that we'd like to be able to do is compact our heap. So if we have objects that are allocated next to each other, and then like the middle one gets freed, but it leaves a relatively small space, it would be more convenient from a fragmentation perspective to just be able to move objects and pack them together. And once we get into garbage collection, we'd like to be working in a programming language where the user doesn't necessarily have access to pointers directly, and so we can go rewrite references in memory. We can change out from under the user what the actual numeric values of their pointers are, and since we're not telling them those values anyway, they'll never notice and their program will keep working great. So here's the sort of general idea of compaction. So as I said, we have our heap, and our heap is kind of fragmented. We have a bunch of little objects allocated and a bunch of little spaces between them. We want to allocate one big object and it won't fit in any of the little spaces. We could request more memory from the operating system, but there's enough space here that if we could use all of it, we could fit this string. So the way we solve this problem is by moving the objects. So we're going to take the objects and move them in memory, and we're going to go ahead and update the references to that object. We could do that through an indirection table, which is sort of what this is implying here. Or, during the process of garbage collection, we have to go identify objects in memory anyway. So we're going to get a list of what all the objects are, where they are, and what all the references to them were. We can just go back and update all the references, although having a data structure that does that effectively is non-trivial. But rather than just trying to move things around, if we do this copy collection concept, we can do a little bit better even than that. In fact, we can do something amazing. So the idea here is instead of having sort of our heap as one big chunk of memory where we allocate things, we're going to start by saying that we're going to use twice as much memory. We're going to have a region of memory where we allocate stuff, and a region of memory that we just leave empty that is the same size. And when we do garbage collection, what we're going to do is we're going to copy things from the start space, which is where we had been allocating things, into the end space. And that works as follows. We start at the roots, we figure out what objects are still alive, we copy the objects from the old location in memory to a new location in memory in the other part of the heap, and then we're going to update the pointers, or the references, that point to those objects so they point to the new location. Doing this in the presence of multiple threads gets a little bit tricky, but there's solutions to the problem. Now, we're going to go ahead and copy the whole list, and eventually we end up with all of the alive objects referenceable from the roots are over here in the end space. And actually, one really cool thing just happened that I want to point out explicitly, and that is that our linked list here got copied into our heap in packed traversal order. So one of the problems with data structures like linked lists and sort of trees in general is that they tend to end up all over the place in memory. Instead of, like with a vector or an array, everything's nicely packed together, and so you get good cache behavior, and the CPU can make the assumption that things that you're going to access close to each other in time are going to be close to each other in memory address. Not true by default with linked lists and trees. But if we're using a copy collector, a copy and garbage collector, then as soon as we run the copy and collector once, any linked lists that we have allocated, and similarly any trees that we have allocated, we're going to traverse them, right? And as we traverse them, we're going to copy the linked list cells, and we're going to copy them right next to each other in traversal order. So now these are right next to each other in memory, they'll be right next to each other in cache, and we took a data structure that had some memory inefficiencies, and we've solved that problem to a large extent just because we're using a copy and garbage collector. All right, but here's the super cool trick with a copy and garbage collector. So we just scanned, we did our mark phase. It took exactly, or asymptotically, it took as much time as it did with a sort of traditional mark and sweep garbage collector. So we had to go ahead and look at every single live object. We didn't have to copy it, but that just means that instead of just doing a read, we do a read and then a write, and writes are not any more expensive in memory than reads are. Here's the trick. After we copy all the stuff, we rename the two halves of memory. So before the start space was over here, now this is the end space. Now the start space is where the end space previously was. And once we swap those two spaces in memory, we can just declare the old start space, the new end space, to be empty. It doesn't cost us any computation time to free any objects. We didn't call free on these objects. We just declared this end space to be empty, and in not linear time, not logarithmic time, not even constant time, but literally 0 time, we just freed all of our garbage objects. And 0 is a kind of amazing number. This is better than we can even do with a manual memory allocator. Free always at least takes the time to do a function call. With a copy collector, free takes 0 time. We spent linear time in terms of the size of the alive objects scanning and copying, but if we have some usage pattern where we allocate a gigabyte of data and then 99% of that becomes garbage, and we allocate another gigabyte of data and 99% of that becomes garbage, we aren't spending any time on the garbage. So this has some advantages compared to traditional mark and sweep. We get compaction, we get 0 cost free, but this just got way trickier. We're updating pointers. It's not obvious how we could deal with this in threads. We do have to deal with the data structures to update all the pointers. Copying the data isn't actually any slower. It's the same time as the mark phase took before, but updating the pointers, it's not even obvious how to do that. It's possible, but it's not obvious. We'd like to optimize this even more. So the next trick that we can do is we can notice a sort of real common property about objects in computer programs, and that is that object lifetime tends to be inversely correlated with likelihood of becoming garbage. Young objects tend to die before they get old. More specifically, the sort of thing that makes this obvious is you like to call functions, allocate objects in the functions, and then return from the functions, but the objects that you allocated were only referenced by local variables, and so when you return from the function, the local objects that you created go out of scope, and you have immediately made them garbage. That happens all the time. So if we can manage to take advantage of that, we can get a significant speed up. And Java was one of the places where this was sort of made an industrial reality. In fact, all of these ideas are applied in even the simpler Java garbage collectors. So let's look at an older, simpler Java garbage collector. These slides are like 10 years old. These slides even talk about more complicated garbage collectors than this. But the basic idea for a lot of the garbage collectors that lots of systems use, they end up looking kind of like this. So instead of just having two segments, the way we did for the copying collector, where we had the young and the old, or the start and the end. Sorry, we have the two sections, the start and the end, the copying collector. Here we're going to have a section called Eden, where we allocate new objects. If an object survives a collection in Eden, it'll end up in one of these two survivor sections. We'll use these two survivor sections as a traditional copying collector, but if an object survives in the survivor sections for a couple of collections, it gets promoted to tenured. Once it's in tenured, we don't look at it for as long as we can get away with it. So we have two different kinds of garbage collection. We have, what were they called in the thing? They're called minor collections. They happen frequently, and they don't look at tenured objects. We have major collections. They happen when we really sort of start to run out of memory, and they do look at the tenured objects, and they clean them up if they've become garbage, but they rarely have become garbage. If you survive 5 or 6 garbage collections, you're probably going to survive 100 garbage collections. So here's an allocation sequence. We're allocating 5 objects here. 2 of them are garbage. Eden filled up, so that's going to trigger a minor collection. We're going to sweep over Eden and the 2 survivors, and the objects that are still alive get copied into survivor 1. We allocate more objects, garbage collect, those get copied into survivor 1 too. Allocate some more objects, garbage collect. Now, before we garbage collect, some of the objects that got into survivor 1 before may have died. So when we do this collection, survivor 1 was full, and so we are going to, instead of copying from Eden into survivor 1, we're copying from Eden and survivor 1 into survivor 2. We sweep, all of the objects end up in survivor 2, we clean out Eden and survivor 1. Eventually, once enough objects have, or once we've done enough collections, we've copied objects from survivor 1 to survivor 2 and back again a couple of times, we'll start to make the objects that survived that long get tenure, and then we don't fire them unless something unexpected happens. And that is sort of a reasonable portrayal of what at least what a single-threaded, modern-ish garbage collector would look like. So with this, we're getting a separation of young and old. We're taking advantage of copy collection. All the benefits of copy collection show up in this system. And then the next problem, of course, is what do we do about the fact that we've had multi-core computers for almost 20 years now? And there's sort of 2 approaches that we can take, and I think the slides get the names backwards for the Java VM. But the 2 approaches that we can take are either optimizing for throughput, So we want to make sure that if we have a big batch job that we're going to do, where we're going to run a program, the program isn't interactive, it's going to run and process a lot of data, we want that program to terminate as quickly as possible. We don't really care about garbage collector pauses. There's not really interactivity. And for that, the way we want to deal with it is we want to do stop the world. So we'll run the program for as long as we can until we need to do a garbage collection. When we do a garbage collection, we'll stop all of the threads that are doing normal work, and then we start up as many threads as we can to do garbage collection in parallel. The other strategy is for applications that do care about pauses. And one thing that a lot of people have probably done are used, which is a Java program, is the game Minecraft. And in Minecraft, you really are sensitive to having pauses. A garbage collection pause in Java can be anywhere from 50 milliseconds to 2,000 milliseconds. If you're playing a 3D game, 3D real-time first-person game, and you have a pause of 50 seconds, you skipped a couple of frames, but you might not even notice. Whereas if you have a pause of 500 milliseconds, you definitely notice. That is something that you feel every single time it happens. And it's no fun. It could mess you up. So in Minecraft, you have to tune your garbage collector to make it work, and you want to use a garbage collector that tends to avoid these garbage collection pauses, even if it means that the sort of total amount of computation the program has to do over the entire execution time of the program might be greater. You might be using more electricity because you're running your cores a little bit more on every frame. All right, so that's garbage collection, at least according to these slides. And so now we've looked at two ways to accomplish this problem, or accomplish this goal of memory management in a computer program. And so obviously we want to compare which is better, garbage collection or manual memory management. And here's what the slides say. It says the advantage of malloc and free is that it's likely to be faster. We avoid garbage collection pauses, and we're going to use memory more efficiently. I don't agree that malloc and free are necessarily faster than garbage collection. You can do some things in garbage collection that are faster than anything you can do with a manual allocator. For example, you can do a copy collector, which makes it so that freeing garbage objects takes literally 0 time. Free always is going to take some time if you have to call it explicitly. Another claim here is that we don't have pauses. And that's not necessarily true. Imagine allocating some sort of giant tree where you have a helper function that's like free your tree. And what that free tree function is going to do is it's going to do a recursive traversal of the whole tree, and then starting at the roots, it's going to call free on every root, and then it will call free on the next layer up, and then it calls free on the next layer up, and it calls free on the next layer up. And when you call free tree on a sufficiently large tree, your program is going to pause. Well, it goes and traverses the whole tree and frees it. That's the same sort of problem as a garbage collection pause. And if you want to avoid that pause, you have to use the same sort of techniques that a automatic garbage collector uses to avoid pauses, like only freeing part of the tree at once and delaying the rest of the work so that your program can go do other stuff before it comes back and does this large job of freeing a large data structure. It is realistically the case, though, that manual memory management can be more efficient. A lot of the tricks that let garbage collection be faster are things like a copy collector, and the first rule of copy collectors is that you start by using twice as much memory as a thing that isn't a copy collector. The disadvantages of manual memory management listed here are absolutely right. It takes more work for a programmer. You're allowed to have a whole bunch of classes of memory bugs and security issues that are difficult to write, or even completely impossible to write, in a language that doesn't give you direct access to pointers and doesn't make you manage your memory explicitly. Although probably Rust falls in this explicit memory management category and doesn't really have this particular set of disadvantages. So there's trade-offs in design that let you get all kinds of different results. So garbage collection, disadvantages, sort of the opposite here. One important thing is that good performance does require careful tuning. Not every garbage collector is going to have all the properties that you want, and picking a garbage collector that's correct for your application can be difficult. There may not even be a garbage collector out there that's tuned for you. If you had one that was tuned for you, it'd probably be the fastest solution, but just using an off-the-shelf like Java garbage collector, there's a good chance that if you had done manual memory management instead, it might be faster. There's also this security vulnerability issue. Yeah, that's a possible problem, although Java is pretty mature at this point. Now, I talked about garbage collectors for C and C++, and it turns out that that's a thing. There is a garbage collector called the Bohem Daimler Weiss garbage collector that you can plug into your C or C++ program just as a shared library. You say -lgc on your command line, and you get this garbage collector, and then you call gc malloc instead of malloc, and then you never have to call free, and your program will work great. This is a conservative collector, which isn't, which means that it's doing this sort of guessing about which things are pointers, and that can actually be a problem if you're working on a 32-bit system where you're using almost all of the virtual address space. Sort of a random number is likely to point to something that you allocated if you're using your whole address space. On 64-bit systems, that sort of false positive failure to free stuff thing is less of a problem. And so this garbage collector is actually a great thing that I suggest playing with if you ever find yourself writing C code in a situation where you don't have to be super conserving of memory, and avoiding memory leaks is something that you want to do. Another thing to keep in mind, we've talked about a couple of non-standard allocators. The slides talk about TC malloc. That was the fancy thing 10 years ago. JE malloc from Facebook is the fancy thing today. You probably don't want to swap out your system malloc. Most of the major programs that have swapped out system malloc have eventually realized that just using system malloc is easier. I think Firefox is one of the only common applications for a modern Linux system where they ship JE malloc because they think it's better than the GNU malloc. But they do exist, and it turns out that Christo stole these slides from Jennifer Rexford, and there's some other references. And those are the garbage collection slides. So that is the whole story that I want to tell about memory allocation and memory allocators. And next class we'll be starting on with our next topic, which is operating system kernels. It should be fun.